Welcome everyone to a very special edition of NITheCS Seminar with Professor Meleshko giving a talk on symmetries of equations with non-local terms. Just to give you a bit of context, we have we had a very successful conference surrounding these topics, and we've decided to extend the conference with a few more activities. And the first one is Professor Meleshko's talk. We look forward to your talk.
Okay, thank you. Actually, I prepared my presentation. It is because I was told that audience, it will be from many different areas who does not know symmetries. But I look here, it's most participants of the conference. So then I'm sorry if I will be, that I will give some slides which are trivial for you. So because I can see somebody also from different areas, like Zurab, for example, right? So, so I call it as symmetry of equations with non-local terms, but in reality, it will be just introduction to methods for constructing exact solutions. And then last part, it will be last publication that we prepared for equations, for delay differential equations and using Lagrangian, so approach to construct equations. And so as on the conference, it was already several examples. Mostly it is started. So this is Professor Hui. He gave a talk, and it was from mathematical modeling of population dynamics. So then I will also give, because it is easier to have different models in this area. Then I will talk about methods for solving differential equations. As I told, that maybe for you, for most of people, from most of audience, it will be trivial, but I have to do it. So, and then I will talk about group analysis. So I will explain why it is group analysis we need to use, because for usually when we construct solutions, we have some assumptions, but in group analysis, you don't need to do assumptions. You just follow method and you will get solutions. So, and first example, it will be Malthus example. So this is, you can see in 1798, and it was equation. We can get immediately solution of this equation. And so, and there is such kind of knowledge that it's better to have even not good model, but it's better than nothing. So then it is first model for such kind of population dynamics. Actually, it is in Professor Hui, he also gave this example. So this is linear ordinary differential equation. We know general solution of this equation. So this is, if you have initial data, you can get immediately solution. And this model is not good. Why? Because this is general solution, because there are some defects. For example, the population is growing exponentially, and the model does not take into account many things, for example, overcrowding, shortage of food, and so on. Then next step for such kind of modeling, so it is when parameter lambda becomes nonlinear, or equation becomes nonlinear, but parameter is linear. So, and then we also know solution of this equation, general solution, if you have initial data. So then solution, it will be the following. And of course, here advantage is that solution does not tend to infinity. You have, it can convergent to some constant, and when t tends to infinity. But also there are some defects. So the population grows monotone, and the population immediately reacts on the change of population. So then next step. So the next step, it is such that it is included so-called delay. So tau here, it is delay time. And of course, many experiments, mostly in physics, there are some delays. And so then this is reasonable to put in model. And this model, now for this model, actually solution is very difficult to construct only numerically. So, and another thing that I wanted to mention for such kind of equations, that for delay equations, it is initial data are given not at one point. You need to give initial data in whole interval. So, and then you can construct, so this is theorems of existence and uniqueness of solution, something similar like for ordinary differential equations. So you can get a solution in some neighborhood of initial data. Oh, sorry. Uh-huh. K, it is some constant. So some constant, actually, because before it was constant K, and solution tends to this case. Then I just change parameter. So then I included, before it was no delay. It was without delay. But now I put in delay in this. So K is the same as in previous model.
Okay.
So, and solution tends to this K, actually.
Okay.
In previous model. So this equation is quite different than delay equation is quite different than ordinary differential equations. And so anyway, we need to try to solve these equations, and we need to solve methods for solving such kind of equations. Here it is example of calculation. So this is logistic equation. I mean that when parameter is no delay, without delay. And here, this is right side, it is with delay. So this is oscillations, and this is more real. So, and then if you consider such kind that in different, like it was in presentation, in different areas, so it depends on space variable. So then we have to consider equation with space variable, and so it will be like this. Or if you have here solution, the right side, it is function a of x, left side, and right side, it is solution for such kind of equation. Or if you have dispersion, so then you have something like heat equation was then solution. We need to also include area where it came. So then another part of equations that it is necessary to solve. So this, for example, here it is some random variables are included. So parameters becomes randomly, and in this case we also need to construct solutions, and so and such kind of equations. Actually, it is called stochastic differential equation, but in reality this is not differential equation. It is integral equation, because here there are two integrals. One integral, it is Riemann integral, and another it is called, for example, in this case, it is eta integral. So then B of S, it is Brownian motion. So then such kind of integration gives us that, for example, differentiation of composition of functions, it absolutely different than for ordinary differential equations. So then we need to use for modeling such equations, the example I gave, but sometimes even more. So for example, you consider functional equations and ordinary differential equations, then you have mixture of them. So, or for example, delay differential stochastic differential equation. So this is even one type is very complicated, but when it is included many of them, I think that very complicated completely. So then I wanted to say that area of my research. So methods of analysis of differential equations. So you can see that roughly we can separate on three parts, something like numerical analysis, theorems of existence and uniqueness, and methods for constructing solutions. So areas that I will talk about, it is methods for constructing exact solutions. But before, sorry. Before I have to, so this is why we need to consider exact solutions. So, and exact solutions can be considered as a real, describing real process in the framework of given model. So if model is given, so, and if you have solutions, so then you can use them to describe something. So this is a question that it was discussed in conference, that you have some solutions, but how you can describe this physical meaning? So if model is physical, has some physical meaning, solution has physical meaning. So, and as a model for comparing various numerical methods, so, and as a basis for improving the models used. So, and before talking about what kind of solution, so I want to say that solutions also can be considered different types. So, for example, strong solution, it means that you have all derivatives that solution is continuously differentiable enough times such that solution can be substituted in equation and something can be. And generalized weak solutions. For example, if you have some shock waves, so it's possible also to describe, then you have to generalize strong solutions. And for example, this is the Hopf equation, and this Hopf equation, it looks like very simple, but we can see that we need to generalize solution, definition of solution, because if, for example, initial data are u of 0x equal to just x, then we consider time is growing. So then solution has no discontinuities and it will be constructed in whole area. But if you just take minus x, so then solution will have some discontinuity. And so this is along characteristic in this case, because right side is equal to 0, characteristics will be straight lines, and along characteristics, solution is constant. So then you can see that at one point, for example, at this point, you have many values, and so this means that how to consider in this case solution. So then it is there are several ways how to do, but I won't do it because my part is related with exact solution. My part is related with strong solution. So this means that we assume that we have enough sufficiently different, so continuous differentiability of the functions. And this is example that for necessary to have this is example when it is traffic jam is described by the Hopf equation. So before I told that in Bangkok we have very bad traffic, and this is can be one of models to describe. So here we have reaffection wave. So this is if you have red so this is, then we can see that cars started stopping and you have shock wave. Then instead of red it will be green. So then you have reaffection wave. So, and solution, this solution consists of several continuously differentiable parts. So you can glue them and you can get more general solutions. As I talked about weak solution. So, and meaning of exact solution also it was changed. So long time ago it was just formula, but if you can substitute the equation and then you can check that this is a solution. But later it can be such that it is reduced to ordinary differential equations. So we think that ordinary differential equations are easier to solve. Then if you reduce to ordinary differential equation, then you found exact solution. So it is not a formula. So why it was for ordinary differential equation? Because numerical methods for ordinary differential equations now develop very good. So then you can use them. And later it was also next step, so if you can reduce number of independent or dependent variables, we can also say that we have exact solution. So we simplify problem. So what kind of methods? And in university we studied Cauchy method. Cauchy method, it is method of characteristics when you have first order partial differential equation, and instead of solving partial differential equation, you can reduce to differential equations. And as I told that ordinary differential equations are good for. Oh, okay. Okay, thank you. Sorry. Then separation of variables. We had also some examples on conference separation of. So then traveling waves. I will give later examples of such kind of solutions. So then multiple waves using dimensional analysis. Also, it was in our conference. It was some representatives for solving such kind of solution and using scaling group. And I told on conference about method of differential constraints. So, and then mapping equations to the well-studied equations. So, for example, linearization problem that we heard today. So this is equation can be linearizable. So sometimes it is not necessary. Is it because we can answer questions that equation is linearizable, but how to linearize? So this is you need to solve some such kind of equation, for example, Riccati equation, which is not solvable in general case. So, but it is good to know that equation is linearizable. So, and finally, I will talk about Lie group analysis and applications of Lie group analysis to integro-differential equation. This is a method of characteristics. I think that everybody who studied partial differential equations in university knows this, that it is reduced to system of ordinary differential equations. It is doesn't matter that it's linear, quasi-linear equation, so you can do. And then separation of variables. So here, this is example. On conference also, it was example given for the heat equation. So this is the heat equation and assumptions. So we separate variables. Actually, keyword here, assumption. So we assume something and then substitute in equation, and we can separate these variables, and we can get that left side is constant and right side constant, and so we can get solution in this case. So more general types of equations, it can be found in Miller's book. So this is and another type of solutions. Also in conference, it was like soliton wave. So for KDV, you can consider solutions of the assumption that solution is traveling wave. So when x minus dt, d is constant, substitute in equation, and you can integrate this equation 2 times. You will have several constants, and if you find some special relations between these constants, and then you will get solution which is called soliton solution. So this is a picture of two. They interact, and it is interesting that soliton after interaction, so they become the same as before interaction. So more general type of solutions, it is when we have linear combinations of dependent variables. So they are called also traveling wave, because if you consider only 2 independent variables, so then it was simpler, but here many. And example also, just one more time, assumption first, and after when you get assumption, so you substitute in equation and you have to do compatibility analysis. So it is for all of methods almost. And then next it is so-called multiple waves. In gas dynamic equations, there's very well-known case. It is called Riemann waves. So then Riemann waves, it means that rank of the Jacobi matrix is less than number of independent variables. So then it will be such kind of multiple waves. And in particular, which are very well known in gas dynamics, it is Riemann wave. It is for one-dimensional case, so one space variable and one is time. Prandtl-Meyer solution. So then they are even up to now. So these solutions are used. For example, I worked in a research institute in Institute of Theoretical and Applied Mechanics, and up to now, these solutions are used to describe experiments which are in some tubes. Later, I will show some. So, and dimensional analysis. So this is David Mason. He told about particular case of dimensional analysis. For example, you can measure in kilometers or meters, so then you can scale, and this scaling, it gives you analysis of solutions, and this it can be found in Sedov's book, for example, and you can see that first edition, it was in 1943, so now it is many editions, so 9th edition in 1993. And this is example of using dimensionless analysis. So for example, this is aerodynamic tube, and we can reduce length of this. And so then I want to say about self-similar solutions. So self-similar solutions, it is more general than solutions which are obtained by dimensional analysis. It is solutions are constructed by scaling group. So one of examples, it is scaling group. So then also there are some assumptions. So assumptions, representations of solutions. These assumptions, they are found using analysis of dimension. So, and then after this assumption, it is substituted in equations, in gas dynamic equations, and then we can get ordinary differential equations. And these ordinary differential equations, this is interesting that it's possible to solve, not completely, but it has some integrals. And these integrals helps, for example, first nuclear bomb, energy of first nuclear bomb, it was found by using this solution. So, and the method of differential constraints. In my presentation on conference, I also talked about this already. So this is my advisor. He invented this method, derived this method. It consists of the following. You have system of equations. Then you add additional conditions, so additional differential equations. And now it looks like you overdetermined system. It is more complicated, but in reality, not, because you have more conditions. So then it is sometimes easier to find solutions. So this means that invariant solutions and some other types also are parts of this method, if you require some special conditions or evolution of system. So this is one of examples that the following, that it's possible to, if you consider gas dynamic equations, then if you consider Riemann waves, so which are used in experiments, so then in this case, solutions are isentropic. So entropy is constant. But the question is it possible to construct by this way solutions which are non-isentropic? So answer is no. In this case, it's possible, but if you use method of differential constraints, it's possible to construct them. So they satisfy some partial differential equations. So if for Riemann waves, right side is 0, for not Riemann waves, so this is particular case. And so you can see that all methods that I mentioned, they consist of several steps. So first step, you have to do assumptions. How to do assumptions? It depends on person. So for example, we had several years ago, there is some solutions in engineers they constructed. So how they constructed, they don't know. They have something, some numbers, so they used. And finally, we found that it's possible to use method. So, and it's possible to construct such kind of solution. So the most important assumption. Yeah, thank you. No, you cannot get all solutions. So you have only particular solutions. Yeah, this method, they are only for particular, except Cauchy method. So I mean that is except that method of characteristics. Method of characteristics, it is for general type of solution. So, but if you can solve ordinary differential equations, so. So one more time, assumptions, substitution into equation, use compatibility analysis. So all of these methods, they have these 3 steps. So question is, how does one get assumptions? So, and answer is one of the answers, of course. So that use group analysis. And group analysis was developed by Norwegian mathematician Sophus Lee, and in the previous century. So then it was forgotten for a while, and Soviet Russian mathematician Lev Vasilyevich Ovsyannikov, he started applying this to mechanical problems. Now it is what we have conference with using group analysis. So and this is example how to use for the same example as we had the heat equation. So we have transformation. So transformation of dependent variables, independent variables, and this transformation is such that it transforms solution into a solution. So after that, we can construct some.
So can I ask that we actually go slowly through this? Just
okay.
Because for non-experts,
Okay.
even the symbols sometimes can be new. Just on this example.
Okay, I will explain. So this is we have heat equation. Then we need to find solutions. So what we are doing, we try to find some transformations. Transformations, it is they have parameter, and we say Lie group because they compose Lie group. And this transformation, for example, here, so tau, it is new time, and A is parameter. So we scale them. So, and then actually question is it possible to find such, because it's nonlinear equation for them? It's possible. It's possible because instead of considering nonlinear equations or nonlinear transformations, it's possible to consider some they are called generators. So, now it is called symmetries. So there is one-to-one correspondence between transformation, between this part, and between generator. So question is how to find. We have some equation. So we have, this is equation to find transformations. This is particular case. So equations are much easier than original equations. Why? Because in this case, we have overdetermined system of equations. And first and second, this system for coefficients is linear. So then it is easier to find solutions. So solution found, after that we can use algebra. So just linear algebra. So spaces, subspaces, and this will give you some set of transformations. And very important that it is solution can be transformed to a solution. So you can start from some simple solution, do this transformation, it will be solution of the same equation. So this means that you can produce new solutions from started point. So, but here we don't need. So I wanted to, for this example, I wanted to say that you don't need to do assumptions. Just plug into this formula, you will get a solution of overdetermined system of equations, which is easy. When you found it, you will use linear algebra, and so spaces, subspaces, and then take one of subalgebra or some subspace. And for this subspace, you can construct solution. So, and it will be, so you will have representation of solution. So you don't need to guess. Do it, and you will get representation. So, and okay. So this is example for the heat equation. For example, for these transformations, we can find invariants. So this is a method, several steps. Find invariant, substitute this into representation of solution. So this is invariance. Invariance, it means that they are not changed using this transformation. So then you will get representation of solution. Some invariants are functions of other invariants. So then this is somebody can guess, but here we don't need to guess. So follow this method and you will get such kind of representation. So then after that, next step, after when you got representation, substitute an equation, and so you will reduce number of independent variables for this case. So, and for this is example how it is substituted, and then finally you will get solution, which is fundamental solution. So from this case. And on this example, we can see that how group analysis is working. So you start from some differential equation. So here X independent variables, U dependent variables, and P are derivatives. So then you have to find admittedly algebra. For this, you have method. So you just substitute an equation. So solve this equation, of course, if you can, but you can because usually system is over-determined system of equations. It's easier to solve than original equations. And after that, choose subalgebra. And for this subalgebra, you can find invariance. So, and after when you found invariance, you can take to represent solution. So representation is invariants are functions of invariance, and substitute in equations and do compatibility analysis. Actually, for invariant solutions, you don't need to do a compatibility analysis because system will be compatible. But if you have some partial invariant solution, so then you need to do compatibility analysis. So this is here books that I started from Ovsyannikov, so 1978, then Peter Olver. So this is handbook of Lie group analysis, where collected all results, maybe all, I think that not, but many of the results collected in these volumes, 3 volumes, up to 96. And so then Ibrahimov's book, and so in my book, so then, and this last one, it is included so applications for group analysis for equations with non-local terms. So then, and my talk actually here will be about, mostly it must be about this case. So, but I had to prepare audience for what we need to do. So then I didn't expect that mostly it will be from conference. Who knows already? Okay, so then applications so for differential equations it was developed, but question is what to do for equations which non-local with non-local terms. So this, for example, is integro-differential equations and delay differential equations, stochastic differential equations, and numerical schemes. So then now it is developing and applying, and so such kind. And then I will talk about this. So this is if you use for differential equations, then you have differential equation, then you have to do several steps, as I told. So you have generator, then use equations, determinant equations, and then question is how to construct determinant equations. So this is after transformation. So you have initial function, then you will transform this function using change or this change. So, and then substitute in equation this transformed function, and we require that this function will be a solution. So we start from some solution, and after substitution, it will after transformation, it will be also solution of the same system of equations. Then we can use the differentiation with respect to parameter, and differentiation with respect to parameter gives us determinant equation. This was for differential equations. Actually, there is one-to-one correspondence for differential equations. So if you have solution of determinant equation, you can go back and say that you have, so you can, I mean that if you have determinant equation, so then you can construct generator. So, and quite opposite. So solution is transformed to a solution. But for integro-differential equations, this is not so. And the question is then what, how to be for integro-differential equations. Then we can do something similar. So, but what does it mean similar? So when we construct for differential equation, we use inverse function theorem. Inverse function theorem is local. So then when you consider integro-differential equations, you cannot use because there are no non-local theorems in general case. So then, but for a while, assume that we can do it. So plug into transformation. So they require that solution is transformed to a solution. Then differentiate with respect to parameter. You will get determinant equation. Then forget about previous part. It was for differential equations. It was like this. So it was. Now you can see papers where even they don't know about that. It was obtained from for differentiation with respect to parameter.
So we don't begin with a known solution. We begin with something we assume is a
solution.
But it's not. We don't need to find the first solution to begin with.
The most important question, transformation. So you will start from some function. Then you have Lie group. Then using this Lie group, you will transform to another function. So this is not related with solutions. And then when you want to construct determinant equations, then you will start. So this is not arbitrary function, it is solution. And then you
do I have to find a particular solution or?
No, general case, not particular.
Okay. That's what I'm asking.
So after that, when you apply this, so then you will get only particular solutions. So when you apply group analysis, it does not give, in general case, it does not give general solution. There are some examples, but it is just a few. So then for integro-differential equations, we use, or for delay equations, we can use the same steps, but as I told, we forget. We know how to construct determinant equation, and we forget about previous part. So solve determinant equations, and it will give you Lie group. So Lie group, and we call it admitted Lie group. So for differential equations, it is 1-to-1. So this I just wanted to explain how to differentiate and which one to differentiate. So here I wanted to give some review of applications of group analysis to equations with non-local terms. So this is one method. It was assuming a representation of admitted Lie group or a solution. So then this is can be done. So many scientists, they did this. So, and the next step, next method, so which was used, it is so-called method of moments, but not all equations, they have moments. So this means then we need to do something else, or transforming some integro-differential equation to differential equation, and for differential equation use classical analysis and then return back. So it is also not so many such kind of applications, and we suggested that to use direct way how to use for differential equations. So you have to construct determinant equations, solve them, and then you will get, you can apply for constructing solutions. So the same as for differential equations. So this is, I skip. This is who worked on this case. So some authors who has some results related with applications to integro-differential equations. So as I told that we want to use the same approach. So here, when we try to construct determinant equations, then derivatives of the generators, we need to consider in some other sense, not like derivative. We have to consider in Frichet sense. So, okay. So I will skip this part because there's not so. What about determinant equations? So if for differential equations, as I told, this is it is not complicated. So sometimes complicated, but sometimes not complicated. Mostly not complicated, especially for partial differential equations. But for equations with non-local terms, for example, you can see that this is such kind that function y depends on x, but here y into independent variable, so y of x. So this is Barbas equation. No problem to construct determinant equation. So determinant equations, that just because we know how to do it, just constructed. But how to solve this equation? So I don't know. So then for each equation, you have to invent a new method for solving determinant equation. Not like for partial differential equation. For partial differential equations, you can split equations if you have polynomial part. So then this is, I wanted to give example today I gave on conference. It is, we started from this equation. It is Boltzmann equation, and the Boltzmann equation is reduced to such kind of equation. This equation is obtained by Bobolev in 1975 by using Fourier transform for the Boltzmann equation. And so it was reduced to this one, and he found solution. So, and here I just want to say that today I talked already, so then I don't know how, because audience is mostly from this part. I will repeat. So I'm sorry for audience who was on conference. I will repeat it. This is the same. So then here, very important that this for this equation, there is a theorem of existence and uniqueness of solution if you have initial data, so for some time. And this helps us to construct a solution. So construct a solution of the determinant equation. So because we need to use something arbitrary. And for differential equations, we can do splitting because we know most equations are Cauchy-Kovalevskaya type. So then we know what is arbitrary. If a system is overdetermined system, so then it is different story. And I want to give one example, so that Navier-Stokes equations, they are not in evolution. They produce new equations of the same, but fortunately, so this is new equation does not affect for Lie group, for admitted Lie group. So here, as it told about, this is Boltzmann equation here. This is collision integral. So, and then it is integro-differential equation. So I won't talk about this. And this is solution that was obtained by Bobolev. This solution, there are only two solutions as a formula for the Boltzmann equation. One solution, it is Maxwell solution, but for Maxwell solution, collision integral is 0. So this means that it does not affect. And another, it is Bobolev Krug-Wu solution. Bobolev invented this, derived this solution in 1975, and after that, 1 year later, it was derived by some other scientists, Krug and Wu, but different way. So then here I wanted to say that how we did. We have this equation, we have this generator, so with arbitrary, with unknown functions or coefficients of the generator of admitted Lie group, and then we know how to construct determinant equations. Before I told that these determinant equations are constructed by differentiation with respect to parameter, but we know how to do it. So we don't do differentiation, we just, because we know how to construct the determinant equation. So this is determinant equation. Here, psi are related with coefficients of the generator. And then question is how to solve it. And for coefficients, if I told that for differential equations, we have splitting, we use arbitrariness of initial data. Here also we use arbitrariness of initial data, but we cannot split. So we use something analysis like for proving Cauchy-Kovalevskaya theorem. So this is consider series, and we try to find coefficients for particular cases. So looks like I have to finish. So maybe I will skip this part. I want to stop on one of applications of group analysis related with delay equations. So, and I'm sorry that here, okay. Of course, we apply such kind of approach not only for the Boltzmann equation, we apply it for some other types of equations. For example, this is for high frequency collisional plasma, but for these equations it was constructed solution by Taranov using moment method. So, and we applied our approach and it gave the same result. So then we applied also for example, viscoelastic material. So this is sigma, it is stress, E, it is deformation. So and then it is viscoelastic medium is described by this integro-differential equation. So this is differential part, and here function phi is related with deformation and pressure, not pressure, deformation and stress are related by this way. So then it's possible to use different methods for solving determinant equations. So, but also in this case, we used arbitrariness of initial value problem. So it is very important, as I told today, that, for example, for now it is very popular so-called fractional equations. So but for fractional equations, there is no theorem of existence of solution. So then you cannot get general solution of the determinant equation. Determinant equation, no problem to construct, but solution of the determinant equations, you need to know arbitrariness of solution. So then we applied for more general case. So then integro-differential equations. And so this is, I will skip. Then also it was applied for stochastic differential equations, but stochastic differential equations, I was disappointed because for stochastic, if you construct invariant solutions, so then for stochastic differential equations, it happens that if you use invariant solutions, then it changes Brownian motion. So this means that if you change Brownian motion, this means that equation is changed. So then it will be like weak solution. This I will skip. So then I want to talk about delay differential equations. Actually, about last result that we had for delay differential equations, it is related with constructing Lagrangians. So this is, for example, we consider this the following delay differential equation. Actually, in reality, it is not delay differential equation because we have that second order derivative is here considered at point t plus. So t plus, it is tau is constant. So this is time plus tau. But why it is not delay? Because here second order derivative is located at point t plus, and here also derivative, first order derivative also is located. So this is neutral equation, but we call it as delay differential equation. So here we have shifting, operator of shifting, so t plus tau, and shifting left, so t minus tau, and this function. So this is derivatives, and here this function right side of equations. And so then we know about initial value problem. We know that in this case we need arbitrary function is given on whole interval. So this interval, it's not in order to have solution, so unique solution, you need to give a data not at one point like for ordinary differential equation, but they must be given on whole interval. So then we can apply, so construct infinitesimal generator and extend this infinitesimal generator for shifted values. So then usual way. And so then here, this is explanation how to do it. So we have, this is coefficients of generator, and then we consider that usual shift left, right. So we will get extension of this generator. So for delays, and then apply this generator to equations, the same as for differential equations, and after that consider on solutions. It means that you substitute equations and you will get conditions for this generator. Actually, why it is considered, so this is constant delay. It's possible to do not only for constant delay, it's possible to do for more general case, but this result is given only for constant delay. And constant delay, it is like for numerical schemes, it is constant step, so constant step. And it is necessary to solve the following equation, but in reality, it is not enough because so this solution is so changed. So then you can see that parameter A, parameter of Lie group, and then here delay, it will be constant. So delay is constant, but you can see that so net is so not good. And so then we consider only such kind of when this function Xi, it is related with independent variable, is linear. So, and next, why I wanted to say it is about applications for Lagrangian. So we consider that Lagrangian has the following form. Here we have element with delays in Lagrangian. Then we require that this is not, so usual way we we variate. So here variation is with respect to Lie group. So then it must be some necessary conditions for this Lagrangian. So this is this one, and here this is written in this form, but in details it is written like this. So this is, here we have derivative with respect to original time and delay time. So and this condition usually it is used, and then variation of Lagrangian. So we variate, we include this is time t, and we variate this with respect to some function. This is variation, it is called so horizontal, and so this one it is with respect to dependent variable. So this functions usual, so this is usual way for variation. So we consider that this is functions are defined on some small interval, so but arbitrary, and outside of this interval it is 0. So we vary a little bit, and then we can consider some minimum conditions. So then finally it will be the following. If you use variation, then it will be the following properties. And here, because functions phi and psi are arbitrary, so then we need to do the following, that we have two different types of variation. So we have, if phi is equal to 0, we obtain, so this is vertical variation. Actually, it was done long time ago by Goltz. I don't know why it is forgotten. So it was in 50s something, and we call it is Goltz variation. So, and another it is horizontal variation. So when we have this expression, actually it is interesting that for ordinary differential equations there is some relations between them. So this is, I mean relations between them as the following. So this means that if variation in one of variation is equal to 0, for example, horizontal, then variation vertical, it will be also 0, and quite opposite. But for delay differential equation, it is not so. So for delay differential equations, what we did, we tried to solve the following system of equations. So this is one variation is equal to 0. We consider as equation for Lagrangian. and another variation also is equal to 0. And it is shown that it's possible to solve this overdetermined system of equations, and it's possible to show that one of them, for example, X-Gold's variation is equal to 0, but horizontal variation is not equal to 0. So this means that for delay differential equations, they are independent. So, and finally, we can formulate, so this is Noether's theorem. So this is Noether identity also can be written. This is part related with differential part, so like in differential equations, and part related with delay. So, and it's possible to formulate such kind of conditions for Noether's theorem. So this is, I wanted to finish on this step. And so here, this is books that we can see for group analysis. So I repeat it one more time. Last one, it is applications of group analysis for numerical schemes. So thank you very much for your attention.
Thank you very much. Are there any questions or comments?
Just like in the morning.
Maybe while the audience is thinking about the question, I can ask a non-expert's question. The solutions that you get after applying the group analysis method, what kind of functions are they? Are they always, because in many of the examples I saw they were involving trigonometric and exponential functions, are always expressed using these basic functions, or
it depends. Not? So it depends, but very important that mostly they are local. Actually, you can extend this if you can. So, but this analysis is local. So for differential equations, but we assume that for integro-differential equations, we can extend it, so it is not local. And the example shows that we can, using this analysis, we can reduce number of variables. But, so, but what kind of functions?
Will you have sometimes functions that are expressed in terms of integrals, for instance?
Yeah, it's possible too,
okay.
Because you will get, for example, second order equation, and then solution of this second order equation, it must be some special function. So
thank you.
It is not only for delay equation, for integro-differential equations, but it is also for differential equations.
Yes.
Sorry, could you specify Blumen? Please, is there?
I have it.
What is your reason?
Oh, not here. Okay. No Blumen here, so I'm sorry.
Yeah. I mean, we can all be friends and cite each other and only fair for everyone.
Sorry, Anka. Oh, sorry, Stefan.
It's only fair to everyone to have a more comprehensive list of references that cite each other.
Yeah, so this is in my book I have. So of course I have. This is in this. Not a lot. Only references that I used. So this means that I used Olver. So unfortunately, books that Bloom and Kumei, I did not read, so I cannot use it here.
I have a problem with that. For example, I have not read much of the book, but I always try to.
Yeah. I agree, completely agree.
I'd like to see
yeah, I will do it.
So speaking about references, we will have an informative, useful session about that right after the seminar. If there are no further questions or comments to the speaker, then we can thank the speaker again. Thank you.